Now that we've looked at two different ways to to simplify an expression or change an expression's form by factoring, we are going to look at two more methods. The first of them being factoring whenever you have x squared plus bx plus c. We're going to use something called factor sum tables to do that. So if we first look at this first question, which asks us what type of problem would give us an answer of x squared plus bx plus c. Well, if you think about what we've learned so far, we've learned that this is a trinomial. So if I'm trying to figure out what type of problem would give me a trinomial, I start thinking about factoring gives me a way to undo a problem and turn it back into multiplication. So some kind of multiplication problem should give me this. And I am familiar enough to know that a binomial times a binomial, to be specific, is what gives me this. I get that by doing first times first, outside times outside, inside times inside, and last times last, giving me x squared plus 7x plus 3x plus 21, combining like terms, giving me x squared plus 10x plus 21. So notice I do get that type of answer when I have a binomial times a binomial, and notice that in the front of each of my binomials is an x term, because x times x, that first times first, are what gives me that x squared, with specifically an x squared with a coefficient of 1. Remember, if there's not a number written out front, it's like there's a 1 there. So when we are factoring something in the form x squared plus bx plus c, again, our goal is to get a multiplication problem, and we do that by unfoiling, since the way I got x squared plus bx plus c was by using FOIL. So here's what we've learned so far about factoring, and what we've learned so far are the steps that we're going to take when we're trying to factor something. The first thing we will always ask ourselves is there a GCF? If there is a GCF, we must factor that out first. After we factored out a GCF, if there is one, sometimes we're done, but sometimes there's more to do. So after I factored out a GCF, I'm going to ask myself, or if I can't factor out a GCF, I'm going to jump to step 2 and I'm going to ask myself, do you have a perfect square minus a perfect square? If yes, you should use a special formula. Remember that special formula was that a squared minus b squared factors to be a plus b times a minus b. If you do not have a perfect square, minus a perfect square, the next thing you will ask yourself is, do you have a trinomial with a coefficient of 1 on the x squared term? So in other words, something in this form, x squared plus bx plus c. If yes, you are going to use something that we call a factor sum table, and I'm going to show you how that works in a moment. Right now I'm just going to kind of record underneath here a little reminder that a trinomial with a coefficient of 1 on the x squared term looks like x squared plus bx plus c. A little bit of additional information to add on to my step 3 of my flow map. So what is a factor sum table? That is when... So here are my steps to using a factor sum table. So my steps for factoring x squared plus bx plus c with a factor sum table. All right, step 1, we are going to put an x in the front of each set of parentheses, because as we like we just looked at, if I have the x in the front of both sets of my parentheses, those first times first do multiply to give me that x squared. And then notice that also, just to give a little bit of background of where this factor sum table is coming from, that these last numbers add to give me my middle term, and these last two numbers multiplied to give me my last term. So for that reason, when we do a factor sum table, we are always going to do factors of the last, which will be the constant term, because we always want to make sure we're in standard form, with the sum of the middle, my linear term. Once I've made my factor sum table, what I'm going to do is whatever numbers I get, they will be the same numbers on both sides of my factor sum table. I already know there's an x in front here, I'm going to put those numbers into my parentheses. So let's look at an example of how this works. So if I look at this first example here, I'm trying to factor x squared plus 10x plus 21. So according to my steps, step 1 tells me to put an x in the front of each set of parentheses. So I'm going to do 2 sets of parentheses with the x in the front of each of them. Then step 2 tells me to make a factor sum table. So I'm going to do factors of my constant term, which is my last term 21 because I am in standard form. And I'm going to do a sum of my middle term, which is 10. So I want to come up with 2 numbers that multiply to give me 21. Factors are anything that multiply to give me the value that I'm looking at, and a sum of 10. Sum means addition. So this table here is basically just a place where I can do some trial and error work. So maybe I say, well, I think 21 times 1 gives me 21. But then I must ask myself, is 21 plus 1 10? And no, it's not. It's 22. So even though these 2 numbers worked for the first half of my factor sum table, they did not work for the second half, and it does need to work for both. So then I might try something else. Well, I'm pretty comfortable with my multiplication facts. The more comfortable you are, the easier this process is going to be for you. And I know that 7 times 3 is 21. Well, then I check over here, and does 7 plus 3 equal 10? Since it does, these are the 2 numbers that I'm going to place inside of my parentheses, giving me a final answer of what is this in factored form? Well, it's x plus 7 times x plus 3. And again, my goal of factoring is always to get a multiplication problem, which I have now done. We're going to look at a total of 4 examples. I want to go through 2 more, and then I'll give you an opportunity to pause the video and try one on your own before watching me do it. However, if you feel comfortable with the material before that time, feel free to pause at any time and try to work through the problem and then watch me work through it. Looking at example 2, if I think about that flow map I created, I check for a GCF. There is not anything that all 3 of these terms can be divided by. I do not have a perfect square minus a perfect square. I do have it in the form x squared plus bx plus c. In this case, my b happens to be -8, but that's okay. So I'm going to go ahead and set up my parentheses with an x in front of each and do factors of my constant term 12 with the sum of my middle term -8. Don't forget the sign belongs to the number. Well, I'm going to try 4 times 3 and I get 12, but I see that 4 plus 3 equals 7. In fact, whenever I add 2 positives together, I'm always going to keep the sign of my bigger number, and if they're both positive, that means my answer is always going to be positive. Well, that causes a problem since I need my answer to be a negative. But notice that over here, my factors have to multiply to give me positive. Well, I know a positive times a positive gives me positive, but I already said that adding 2 positives is going to give me a positive, so it screws up my sum side. Well, doesn't a negative times a negative also give me a positive? So what if I tried something like -4 and -3? Those both do give me a positive 12, but again, notice -4 plus -3 adds to be -7, so I'm close but still not right where I want to be. Well, what if I try -6 times -2? Well, that does give me a 12. -6 plus -2 does give me -8. So it looks like -6 and a -2 are going to be the numbers that give me the result I want, giving me a final answer here in factored form of x minus 6 times x minus 2. Looking at example 3. So first thing I always ask myself is, do they have a GCF? And I notice that all 3 of these terms can be divided by 2. So I'm going to take my GCF and put it out front, and 2x squared divided by 2 is x squared. 10x divided by 2 is a positive 5x. Positive 12 divided by 2 is a positive 6. Now, sometimes when I take out a GCF, I'm done, but I have to check. So I ask myself, can this polynomial, this trinomial here, inside of my parentheses be factored any further? Well, yeah, it can, I think. It looks like I might be able to try a factor sum table with it since it's a trinomial with a coefficient of x squared. I'm going to, for the time being, ignore the 2. And I'm going to go ahead and set up a factor sum table using this information right here. So doing that, I'm going to say I'm going to leave the 2 out front. I'm going to put an x in the front of each set of parentheses, and I'm going to do factors of my my constant term, my last term, with the sum of my linear or middle term, 5. Well, trying to think of two things that multiply to give me 6 and add to give me 5. I might try 2 times 3 does give me 6. And notice 2 plus 3 does give me the 5 I'm looking for. So I'm going to go ahead and put a positive 2 and a positive 3 in here, giving me a final answer of 2 times x plus 2 times x plus 3. I would like to look at one final example on this topic. Now would be a good time for you to go ahead, pause the video, try it on your own to see how successful you can be. Once you finish completing it on your own, go ahead and push the play button and follow along and see if your steps match mine. Okay, now that you've had a chance to do that, I'm going to go ahead and first ask myself do I have a GCF? I do not have a GCF for all three terms. I also do not have binomial minus binomial. I do, however, have a trinomial with a coefficient of 1 on my x squared term. So I'm going to go ahead and set up x in the front of each set of parentheses, and I'm going to do factors of negative 54. Don't forget the sign belongs to the number with a sum of 3. Well, I know that in order to get a negative, I'm going to have to do a positive times a negative. And since I want my addition problem to be positive, my bigger number better be positive. So I'm going to go ahead, and maybe you had to go through some trials, and that's okay. The whole point of this table is to give you some space to do some guessing. I get 9 times negative 6 is negative 54. 9 plus negative 6 equals positive 3. So I'm going to go ahead and put my positive 9 and my negative 6 in here. Because the commutative property tells us it does not matter what order we add and subtract in, I do want to point out that this is the same thing as saying x minus 6 times x plus 9. Again, because the order we multiply in does not matter.